Global internet traffic now exceeds 2 zettabytes per year. Pushing these massive streams through physical copper wires and fiber optic cables hits a hard ceiling. Data in transit faces 3 constant operational threats: the strict bandwidth limits of physical cables, adversarial interception from outside actors, and latency over vast geographical distances. Building wider cables or faster routers eventually meets the limits of physics. Scaling the internet requires manipulating the data itself using algorithmic mathematics. This manipulation falls into 3 core categories of data transformation: compression, encryption, and hashing. We can squash the file size to fit narrow bandwidths, scramble the contents to protect from interception, or collapse it into a fixed code for instant verification. The mechanism that separates these 3 tools is the mathematical property of reversibility. Whether data can or should be perfectly reconstructed at its destination determines which algorithm engineers deploy. Solving network bottlenecks is an exercise in deciding exactly what information must survive the journey and what can be permanently discarded. Compression is the process of minimizing a file's payload. A smaller file transfers faster and requires less storage space on the receiving end. This diagram shows a grid of image pixels. To display color variations, each pixel requires a specific color depth. Storing just 8 possible colors requires 3 binary bits per pixel. Multiply that across a high-definition photograph, and the file size increases significantly. Lossy compression algorithms scan this grid and identify neighboring pixels of similar shades. It averages out those variations into a single uniform color, lowering the required bit count for that area. This process intentionally discards data. Once those specific shade variations are removed to save space, they are gone. The algorithm is strictly irreversible. Look at this original, high-resolution source photograph. Now look at the lossy compressed version. The algorithm has permanently removed a massive amount of pixel data, significantly reducing the file size. Human eyes rarely perceive the loss of high-frequency visual details or extreme audio frequencies. By exploiting the limits of our perception, engineers accept irreversible data loss in exchange for faster transfer speeds. Destroying data works for photographs, but applying lossy algorithms to an executable program or a text document is fatal. Lose a single bit of compiled code and the entire file fails. These files require lossless compression. The original data must be shrunk for transit, but remain 100% reversible upon arrival. This is where techniques like run-length encoding, or RLE, come in. RLE targets continuous blocks of repeating data. Instead of transmitting 6 A's, 5 B's, and 3 C's individually, the algorithm replaces the repeated values with a single character followed by its count. RLE struggles to shrink files with little repetition, but it excels at perfectly preserving structure. The receiving computer simply unpacks the count variables, reversing the exact string. For complex text documents, engineers use dictionary encoding. The algorithm scans the document and extracts frequently occurring phrases like "we shall" and "fight," mapping them to a dedicated index. It substitutes the long phrases in the text with index numbers. To ensure the file is usable, the dictionary index must be transmitted alongside the compressed data. Lossless methods don't throw information away. They locate structural redundancies and transmit a set of mathematical rules, allowing the recipient to perfectly reverse the exact original file. Reducing the payload solves the bandwidth problem. But passing that payload across public infrastructure introduces the risk of interception. Encryption is the mathematical obfuscation of data. Like lossless compression, it must be completely reversible. But the critical distinction is that encryption must be reversible exclusively for the intended recipient.
Early digital security relied on symmetric encryption. Both the sender and the receiver share a single private key used to lock and unlock the data. But the key itself must be distributed before communication begins. If an adversary intercepts this key exchange, they capture the ability to decrypt all subsequent communications. Sharing a secret over a public channel inherently risks the secret. To eliminate the key exchange vulnerability, network engineers use asymmetric encryption. This system generates a mathematically linked key pair, one public and one private. the public key is published on open directories for the world to see. The private key never leaves the owner's machine. If you want to send a secure file, you lock it using the recipient's public key. Because of the mathematical relationship between the pair, once locked with the public key, the file can only be decrypted by the recipient's hidden private key. Asymmetric cryptography separates the locking mechanism from the unlocking mechanism. The secret key is never transmitted, which effectively neutralizes the threat of interception. Securing the payload creates a secondary problem. If a public key is available to everyone, how can a recipient prove a message actually came from the claimed sender? The asymmetric key architecture provides the solution by running the process in reverse. Instead of encrypting the message with the recipient's public key, the sender encrypts it using their own secret private key. When the file arrives, the receiver decrypts it using the sender's openly published public key. Because only the sender possesses that private key, a successful decryption by the public key acts as a mathematical guarantee of origin. This reverse process forms the basis of digital signatures. While compression and encryption are designed for eventual reconstruction, hashing operates as a strict one-way function. It maps variable inputs to fixed-length outputs. This permanent irreversibility is critical for password security. When a user creates a password, the system doesn't store the text. It runs it through a hash function and stores the resulting code. During a server breach, an attacker only gains access to a list of hashes. Because the function is one-way, the attacker cannot reverse the code back into the original password. This animation illustrates a hash table, where hashing solves search latency through deterministic mapping. A hash table pairs a hash function with an array of storage buckets. Instead of scanning a massive list row by row, the data itself effectively tells the computer where it is stored. Because the function is deterministic, the name John will always produce the same hash, pointing the system to the exact storage bucket instantly. Occasionally, two distinct pieces of data will generate the exact same hash output, triggering a collision. Engineers resolve this by storing multiple items in a list at that bucket, or using a secondary hash function to generate a new address. Hashing achieves zero-latency data indexing through deterministic mapping, while its irreversible nature ensures that sensitive inputs remain permanently shielded from extraction. Managing the Internet's scale and security relies on applying the precise rules of algorithmic reversibility. On this Cartesian matrix, lossless compression maps to perfect recall, while lossy methods permanently discard data for space. Encryption offers perfect reversibility, securely locking the payload with asymmetric keys. Hashing is strictly irreversible, securing passwords while providing constant time mapping for databases. Together, these three distinct mathematical interventions serve as the invisible scaffolding that securely holds our modern global communication networks together. Mastering information theory requires knowing precisely when data must be perfectly preserved, when it should be locked away, and when to simply discard it.